Right, we begin our discussion by looking at question 2, a discussion that focuses on how to solve this question from first principles. To start with, we understand that this question is question 2, which focuses on the first principles, using what we call the epsilon delta argument, that f of x defined by that is the piecewise function f of x is continuous in x equals 2. Right, so how do we prove continuity from first principles? We get started. So to prove continuity from first principles, we proceed as follows. Right, we note that for each, right, for each epsilon greater than 0, we need to find, a delta positive such that now at this point, so we always begin with epsilon and delta and indicate that they are both positive, strictly positive, such that the absolute value of x minus 2, this absolute value here is basically less than delta. And when that happens, the implication is therefore that f of x minus f evaluated at 2 is less than epsilon. Okay. This is what we begin by writing. Because we want to prove continuity at x equals 2, or yeah, at that point. Although it's set in x equals 2. Okay, it's a point. Okay. Right. So since we first make a certain observations that the number x equals 2, the number 2 itself is an element of the interval x such that x is bigger or equal to 2. We know that, therefore, x is sort of in the part here of the function. We have okay. We have that now we can evaluate this function. So we realize where the x can be 2, x is allowed to be equal to 2 when the part of the function is x squared plus 2, which means we shall therefore have 2 squared plus 2. So we shall not use the bottom part of the function when x equals 2, because the bottom part of the function only works when x is negative, and therefore 2 squared plus 2 is exactly 6. Okay. Moreover, if x itself is now we can start by looking at one of the parts. Okay, so we can look at one of the parts when x is greater or equal to 2, the top part of the function. Then, so we're focusing on this part of the function when x is greater or equal to 2. Then it means that we can have the absolute value of f of x minus the absolute value of 2. Okay, so what is this? At greater or equal to 2, we shall have f of x is x squared plus 2 minus, we agree that f of 2 is 6, so we put 6 here. And therefore this is x squared minus 4. Okay, this is it. Now we perform just factorizations. This is the difference of 2 squares, so we can just factorize this to x minus 2x plus 2. Okay. If x is bigger, x is bigger than minus 3, No, there's not really one to say. Right, so if x is bigger than, x is less than 2. X is less than 2. Okay, that's the second. Okay, but first let's first finish this part. Let's first finish this part when x is equal to 2. It has the most amount of work. Right, so let's get the work done when x is bigger than what? When x is bigger than 2. So we write a lot here because this one now is having a couple of parts. Okay, so this obviously has a series of implications. What does it mean? It means that x is in the absolute value of a product is the product of absolute values, and then we have this. But we understand that we have a condition on delta that x must be what? X minus 2 must be less than delta. And therefore, that means that we have x minus 2 here. So we have good information on x minus 2, but now there's x plus 2 here. So we're going to have this one write as x, written as x minus 2 plus 4. Okay. We want to have a minus 2 in the x plus 2 expression. And therefore, we try to be creative. Right, so we can use the triangle inequality. Right, so the triangle inequality. The triangle inequality will therefore say if you have the modulus of x
Hello.
plus y. Yes, please.
Where did the +4 come from?
Okay, that's a good question. Yes, okay. The plus 4 came from the fact that we want to make, we have x plus 2, but we desire, in view of the condition that x minus 2 must be less than delta. So we want to have x minus 2. So what number can we add? That becomes the question. What number can we add here so that would not change the expression, but we have achieved the x minus 2. We can only add 4. So because 4 minus 2 is 2. Okay. So that is how we reason that out. Right. So moving forward, the triangle inequality, as I indicated, is actually saying that at this point you have the following. So this is the triangle inequality here. Right, so the triangle inequality says that. Okay, so if the triangle inequality says that, what does it mean for us? Well, it says we have the following. X plus y is less or equal to the modulus of x and that of y. Okay, good. So we're good. Right, so we're gonna come here and use it. And we put the round brackets here and put x minus 2. And put x minus 2 and then plus 4, like this. Right. Yes, we're putting the absolute value 4, but the absolute value 4 is just 4. So we have the absolute value just around the x minus 2, which obviously can be a variable. And this is good. This is good. But this is less than or equal to. Okay, we can put less than or equal to. Now, if we choose x minus 2 to be strictly less than 1, we are choosing delta to be equal to 1. Okay, you're going to see what that means. So we're going to have 5 here, and then 5 into x minus 2. Right, provided we say that. This is true provided the x minus 2 is what? The x minus 2 is less than 1. Okay, why x minus 2? Well, x minus 2 because we have here that the modulus of x minus 2, the absolute value, is less than delta. So we are choosing delta to be 1. It's a choice. It's a standard choice for this module. So in general, one can choose delta to be anything, but sufficiently small. 1 becomes a popular choice. And now, because of this, we then say hence. We then say hence the modulus of f of x minus the modulus of 2 okay, the modulus of f of x minus f of 2. We have this. Okay. For all x, in a 1,
I'm lost here.
yes,
Where
okay.
you got the 5 from?
Where got the 5 from? That's a good question. So, okay, thanks for noting that. But we're getting the 5 from the fact that we have x minus 2 plus 4. And therefore, we have chosen x minus 2 to be less than 1, so that we have 1 plus 4, and therefore this equals 5. So ideally, the understanding, therefore, is that the modulus of this, the modulus of x minus 2 plus 4 is less than 5. But with less than 5, we can write less than or equal to. Okay, can also use the strict inequality there. It's okay. Right, so that is where the 5 is coming from, 1 plus the 4. Right, so in other words, we have chosen delta to be 1. Why? How was delta chosen to be 1? We always choose delta to be 1 when we have products, because we want to get rid of the x plus 2, because in view of the delta, we want only x minus 2 to be less than delta. Now, here in the green part, we then proceed to say for all x in a 1, because we chose delta to be 1, which produced the 5, in a 1 neighborhood, in a 1 neighborhood, of 2, in a 1 neighborhood of 2. Okay, so we are in business now, and this means we have this, we have this, we have this, we have this. Given, okay, this means given epsilon positive, choose delta to be a minimum, to be sort of the minimum, or just yes, the minimum of this, of the two. So delta will be the minimum of 1 and the following. So we chose delta to be 1. That's what produced the 5. But we also have the following. Okay, so let's see. I want to
Hello?
write. Yes, please. Yeah.
Why don't you stop here? Why don't you stop there? Why do you continue this part?
Okay, why do I continue that part? Because we want to get the value of delta. We want to get the value of delta, and now we can't stop here because we can't get delta because of the x plus 2. So the x plus 2 now must be dissolved. It is dissolved by making it x minus 2, making it the absolute value of x minus 2. But now we then continue to have the 5. The 5 therefore means at this point, we can write here that this is less than what? Less than epsilon. And therefore, it means that x minus 2 is less than epsilon over 5. So, and that means, therefore, here we can write, so delta now is the minimum, because delta is very small by assumption. And so since it's very small, we choose delta to be, the minimum of the 1 we chose that produced the 5, but also the epsilon over 5 that we got. Remember that whenever we have the absolute value of the x minus, of the f of x minus f of 2 is less than epsilon, we actually have that is less than epsilon. So this thing here, when we work through it and go all the way, it is ultimately less than epsilon, and then we get x minus 2 from it, the absolute value of x minus 2. And then now it means therefore, it means we have the epsilon over 5, epsilon over 5, epsilon. Now, the absolute value of x minus 2 is less than delta. So now, whenever we have the absolute value of x minus 2, we always have, it has to be less than delta, because that's what we started with. So we come here now. The x minus 2 absolute value is less than epsilon over 5. It means, therefore, epsilon over 5 is a possible value of delta. But we also chose delta to be 1, the one that produced the 5. So therefore, we have two values of delta here, 1 and epsilon over 5. So we choose it to be the minimum because it must be the smallest of them, of the two. Now, this is the first part. So we just have dealt with the first part of the function. But continuity of the function depends on, because we say the function is continuous. So a function continuous means that it is without a break over the domain over which the function is drawn. So, and therefore that means that we shall go to the next one. And moving to the next one, next part of the function, we proceed as follows. Right, so let's just proceed now and get the following, Right, and get the following. Right, I wrote this earlier before I came to my class, and just a minute. I used another yeah, I used the draw tool to create this. Now it's can be erased using the usual eraser on the slides, or I'm gonna I can erase it with the tools that created it. Okay, I just want to make my slides clean. I was doing some tests before we started our discussion. Okay. I want to look at the second part of the function. And the second part of the function is this one here. Right, so the second part of the function is this, but also I need to have the thing, the function again, just one sec. Um, recall that. Recall that. F plus 2. If, so we recall just the definition of the function. Plus 2x minus 8. If x minus 2. Okay, now you have this one. Okay, so what do we do with this? We focus now on the second part because we focused on the x equal to 2 part. Now, what about if you focus on the other part? So we say if x now is smaller than 2, because that's the bottom part of the function, we shall have therefore f of x modulus minus f of what? Minus f of 2. And this is equal to? Is equal to, okay. What is f of x now when x is less than 2? It is the rational function plus 2x minus 8. You divide everything by x minus 2. And then f of 2, we got it from the previous thing. F of 2 is obtained by putting 2 into the first part, and therefore is 2 squared plus that, which is 6. Got it before. Okay, this is less, the x is less than 2, so it means therefore this function makes sense, but we can be able to factorize this into x plus 4 into x plus 4 into x minus 2. And then you divide by x minus 2 minus 6. Dividing by x plus what? minus 2, this one. Okay, so we have that now. This is exactly that. And then we agree that this one is less than epsilon. And therefore, we recall that x minus 2 absolute value must always be less than delta. By comparison, the conclusion is therefore that delta is equal to epsilon. Okay, because we compare delta with what we got. So delta equals epsilon there. Right, so that's what we have. So we have delta equals epsilon, and then we also have delta is the minimum before. Then if x minus 2 is less than delta, we have if x minus 2 modulus is less than delta, okay, we have the modulus of f of x minus the minus f of 2, and then this is we saw that is less or equal to 5 into fx minus 2 modulus. This was proved, the 5 was obtained since by choice the absolute value of x minus 2 is less than delta, but delta is less than 1 by choice. And this here is strictly less than 5. What is the absolute value of x minus 2? Well, from the previous argument, we understand that the absolute value is epsilon over 5. We got it before, and this is equal to epsilon. This is true because, or since, the absolute value of x minus 2 is less than delta, less than epsilon over 5. We got it from the previous page in green at the bottom of the screen. The absolute value of x minus 2, bottom left, is less than epsilon over 5. Okay, what is the conclusion out of everything here? Hence, f of x is continuous. Is continuous at x equals 2. How is it continuous at x equal to 2? Well, continuity in mathematical terms means the following. Okay, because how do these arguments really mean the function is continuous? Under what conditions would we have a situation where the function is discontinuous? Okay, how do we see the continuity from these things we've written? We understand that. So in mathematics, when a graph is given, okay, this function is a function of x, is given like this. So we need to first say, and we want to determine continuity at x equals 2. Um, okay, want to determine continuity x equals 2. I'm just putting a hypothetical example, just an arbitrary function, f. Okay, an arbitrary function f. What do we have here? Right, what we then have is the following. Okay, from first year calculus, there are 3 conditions for a function to be continuous. Continuity at x equal to 2, we ask the question. So this is just a development of the theory on continuous functions from the first year calculus module. Right at first year, we first say if it x equal to 2, we need to say f of 2 is defined. Okay, we use the word defined. So the second thing is that the the limit must exist of the function. So we get to the limit because these are just limits when the things are less than when x is less than something. And so we then say that the limit of the function, you can write like this. This limit must exist, and you can write it in 3 steps. You can break it down to more steps, but it's not necessary. Okay, we can just say this limit must exist. Just here, just recapping on that because it's just the mathematicians doing much research all the time and finding smarter ways, but also doing these things from first principles now. It's sort of an advanced thing. So this limit exists. 3, 2, 1. This limit exists. 3. This limit as x approaches 2 of f of x. This limit must equal f of 2. It must equal f of 2. Okay, these are the conditions for continuity. So now it means here we are saying f, the absolute value of f of x minus f of 2. This absolute value is ultimately less than epsilon. Well, in mathematical arguments, this means this. It means the limit of the function f of x is actually equal to f of 2. So it means f of x is actually equal to f of 2. The limit, quite. The limit of the function is f of 2. And that is why less than that's what less than epsilon means. Less than epsilon means f of x and f of 2 are very close to each other, so the difference between them is very small. And that is how we say in mathematics they are equal. It's just another way of saying they are just almost equal in limit terms. In limit terms. Okay, we use this epsilon thing in limit terms. And then we have proven this, and we are done with the proof. Okay. We continue and look at the next concept. Right, did this question because you sent me this question. Right, the next thing we're going to discuss is this one here. The idea of the interval of convergence is it's there in the exam all the time. How do we given a power series? Right, so here we're given a power series. How do we prove that okay, there are 2 questions that we just put here, but now I want you to focus on the first part. I know I've put 2 of them, but yeah, I'm not interested in we shall do that one next. Right. I want us to just find the interval of convergence of the power series. How do we find the interval of convergence of this power series? Okay. We use the ratio test. The ratio test. We shall see how we use the ratio test. In this module, yes, please.
For all our power series questions, do you use the ratio test at the beginning for everyone?
Okay, that's a good question. For all power series, do we use the ratio test for all the series? Well, to find the interval of convergence, we use the ratio test. Okay, the ratio test is used to find the interval of convergence. But now the power series that we study, we can use, I'm yet to elaborate on the many types of tests we can use. Obviously, like the ones we did yesterday, where we were determining the absolute convergence or conditional convergence or divergence, we must try the tests. So the truth is, it is through trial and error of the rest of the tests that we can determine the absolute convergence or conditional convergence. But for the interval of convergence, we use only one test, the ratio test. Okay, maybe to start with, what is the ratio test? Well, ratio test means that if you given a power series, right, given a power series, this one here of an, a 1 to infinity, then we can speak of the limit as n approaches infinity of the an plus 1 over an modulus, right? And this modulus here, this limit must be L. That's the ratio test. So ratio test therefore proceeds to have two conditions, that this limit either is less than 1 or bigger than 1, or this limit can be 1. Okay, we're interested in those three cases. But now if it's less than 1, then we say there's convergence. So the series converges. If it's bigger than 1, this limit, it means the series diverges. If it is equal to 1, then it's inconclusive. Right. So we shall just use this ratio test. Only for the interval of convergence, it works all the time. But now the ratio test works for some series to determine the convergence. Okay, so right, but for the interval, yes, only this one. But I'm here to give a summary of all the tests, and we need to practice more of these power series questions, because sometimes you can look at the question and like, what test will I use to determine if it's convergent or it's divergent? Okay, yesterday we used the P-series test because it's easier. It was easier, but the P-series test works for polynomial kinds of series, or this series whose general term involves a polynomial there. Okay, right. So now we shall practice more. I'm going to bring 10, 20 questions, different tests, and we shall practice with those, and I'm going to mark those and give you the answers to those. We shall discuss them together. Okay, for this one now, we begin by as follows. So for this one, we let an. Normally we change the variable r to n, but it doesn't really make a difference. Right, so we have this one. Okay, and then we have this one, 2 to the power n, and then we have the square root of n x to the power n. So then we have the modulus of this. What is the modulus of this? The modulus removes the -1 to the power n. So we have this. And then we have this. All right. We achieved this. Now, the next thing we're going to do is to have a new thing. So then we define alpha n, even in Hagati. Hagati uses alpha for the ratio test. So now you therefore have the n plus 1, a n plus 1 modulus. Okay. So you have this
Hello.
one. Yes, please.
Why did you remove the -1?
Okay, that's a good question. Why do I remove the -1? We always remove the -1 because the ratio test it deals with positive terms, series of positive terms. So we cannot use the -1 in our ratio test calculations because we must make sure that we're dealing with positive terms for purposes of the ratio test. Always, always. Okay, right. So now we have the modulus of the n plus 1. So it is 2 to the n plus 1, n plus 1, n plus 1. And then you divide. Okay, if you divide by that, you multiply by the reciprocal of that. Okay, doesn't matter. You can just show a little bit more one step division. Right, so we divide and then we multiply by the reciprocal there. Okay, so we're going to divide. We divide by 1 over 2 to the power n, the square root of n, x to the power n. And then now we have this one, which is divided by 2 to the power n plus 1, the square root of n plus 1, n plus 1. And then we multiply by the reciprocal, which is 2 to the power n, the square root of n, right, over x to the power n. And therefore, what is this? Right, so this one now can be simplified. And then this one is simplified as follows. To the power n cancels, and you have 1/2. Then you can write one big square root like this. Just to gather together the two square root terms. And then we have, okay. Just note, please, if you take the modulus, then it's going to affect x. It's going to affect the x. It's going to affect the x like that. Okay, just to note that. So now the n is already is a natural number, so it's a positive natural number. So the n is not affected, but the absolute value therefore has the tendency to affect it affects the x. So we must therefore have that. If we have that, then it is the so here is going to be n plus 1, and there is going to be n, and then here is going to be n plus 1, and then that. Okay. Okay, and then here it's going to be n plus 1. Okay, it's going to be n plus 1. So that is what we get. The right way to practice more on this series. I'm going to give you extra problems on series because they are a little bit tricky because now we normally do by trial and error to determine if a series is convergent. So you try the ratio test, you try the nth root test. Some of the tests are not very popular in this module, like the nth root test. You try the limit comparison test. Obviously, the limit comparison is also very popular here. All right, so you have that, but now we're not done. What else is left? There's only modulus of x that's left. There's only modulus of x that's left. Like this. Now, hence, the limit as n approaches infinity of alpha n n plus 1, okay? And then we take the limit of this using the ratio test. Okay, you can write a trivial step here so that it can make a bit more sense. In view of what I wrote earlier, I can write here, yeah, I can write here like that. And then because we're using the ratio test, how does the word ratio test? Ratio test. Why? Why the word ratio? Well, it's because we are determining the ratio here. Okay, and then the ratio test is used because it has a ratio in it. And then now we have this one here, which is 1/2. And then you have the nth root, the square root. Right, so if we find this limit now, can do strange things with this. Right, so but yeah, I don't do something dramatic. We can take the limit. The limit can be taken to only under the square root and be removed from the front. But one thing that you can do here is to take 1/2 and divide. So you can divide n by n, and then you divide n by, because that is the highest power of n, and then we have this. Okay, this, let's put this back. Bring that to very there, but it is not very tidy. So yeah, okay, right. So we have that.
Hello?
Yes, please.
How did you get this equation?
How do I get that equation? Okay, that's a good question. How do I get that equation? Right, I get that equation from the fact that, from this one. Get that equation from this, because this is divided by modulus of this one divided by 2 to the power n, the square root of n. So if we're dividing by this, because I use the division here, then we multiply by the reciprocal of that. So we invert the 2 to the power n square root of n divided by the modulus of x to the power n. So this one is going to cancel this one. And then obviously this one is going to cancel that, leaving us with only 1/2. And then the square root is going to be left. So you have the square root over the square root. We can just write one square root and divide the n by the n plus 1. And then obviously,
Hello.
yes, please.
How did you get this wait
Uh-huh.
as a numerator? How did you get the numerator?
How do I get the numerator? Okay, another good question. Right, so the numerator is simply because the way the question is given here, this means that you can just write this one is x to the power r divided by 2 to the power r, the square root of r, you know, we can write it like that. For purposes of inverting things, if we need to reciprocate, so obviously the x to the power r is written on the side, but you can write it is the numerator in mathematics, okay. Right, so it becomes therefore the numerator like there, and therefore, because I wrote it now as the numerator here in the green part, because um, for the purpose of inversion, to invert, because now we must see what happens to it now. It goes to the denominator now. Okay, right, so we get that. Okay, think about it. And then now we get this, and we divide here by that. So we write the modulus of x, okay. Right, so this is the limit as n approaches infinity of 1/2. Okay, the highest power, I was dividing here by the highest power of n. So which means that we shall be left with 1 divided by 1 plus 1 over n. When we take the limit as n approaches infinity, it is 1/2. And this is less than 1. Okay. Okay, so we have that. So yeah, we get 1/2. I missed something. I missed something here. I missed x. It's not just half. It's not just 1/2, but there is something else. Okay, um, so you have this, and therefore this is less than. We got 1/2 before. Okay, so but yeah, it's that. Wait a sec. Right. So I want to write properly here. This less than is just too awkward. Right. So we have that. Now, what do we achieve out of this? We have the following. We have the following. Right. So we have here the modulus of x. So it's less than, it is rather equal to 1/2. Not really less than, it is equal to 1/2 because the limit of the square root of that is just 1/2. Okay, so it is equal to 1/2 that. Right, so it is equal to 1/2 that. Equals to the modulus of x over 2. Okay, by the ratio test, we require something. We require that this must be less than 1 for convergence. We want convergence, so we force it. We force that limit to be less than 1. And obviously, that means is less than 2. Um, and put the following words here. And put the following words. So I can say here we have it converges absolutely for. Okay, we have that. I can move to the next page. Right. So we have the following. Right. Thus, the series. Okay, the series that is given, which is this one here. X to the power R converges absolutely for the modulus of x over 2 for that limit less than 1, which means x must be, if you multiply, you sort of cross multiply both sides by 2, and diverges. Right, and diverges for this modulus bigger than, when the limit is bigger than 1, we say the ratio test implies divergence of the original series we are investigating. So it means that divergence is when modulus of x is bigger than 2. Okay. For the interval of convergence, we want to find the interval of convergence. So the interval of convergence is that one. So it means, therefore, that the interval of convergence is this one here. That is the interval of what? Of convergence. Okay, interval of convergence. But most importantly, this one would be the interval of divergence, but we are not interested in that. Interval of divergence. Okay. Next. For x, now we have two things. You see, when we are dealing with the modulus less than 2, modulus of x less than 2, the modulus itself will produce -2 plus 2. So you must investigate what happens at the boundary points of this interval. Okay, it's strictly less because of the condition of the ratio test. We require that for convergence, the limit must be strictly less than 1. Okay, what happens when this is equal to 1? Okay, we always investigate that. So we have, in other words, when x is equal to -2, at the boundary point of the interval. Okay, we shall elaborate a little bit more on that. So, but this means the series here, it means now this is the original series in the question. And then it is 2 to the power r, the square root of r, and then x to the power r. And then you'd have this equals 1 here, -1 to the power r. This is the original one. I'm just manipulating it. But we are substituting into this one here -2 in the place of x. N equals 1. So what is this? Right, so we can play around with this algebraically. Right, playing around, we can extract -1 from the 2. minus 2 to the power r. And then you have 2 to the power r here, the square root of r. Right, we have extracted minus 1 from it. But if you have minus 1 to the power r, minus 1 to the power r is like minus 1 squared. So it becomes positive anyway. Right, so you have, yeah, okay, simplifies beautifully. So this becomes a series here. The minus 1 to the power 2r is just 1. So we're just left with 1 over the square root of r. A beautiful thing because obviously from r, I'm writing n here. Okay, so it doesn't really matter, right? So we can write any of these. The dummy symbol. Can I write one thing, one symbol here because we're using both? So I'm going to remove this one. Okay, I'm going to use this one. Okay, so I'm going to use this one and put R, 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 R. Okay. Now this one here is a P series. Because it is this summation, R equals 1, and then it's 1 over R to the power 1/2. Okay? R to the power 1/2 is a P series, which is a P series. Okay, it is a P series with P. P is the power of the R, which is 1/2. But this 1/2 is less than 1, and therefore, the series, this series here, 1 over R to the power 1/2 diverges. Okay, now, so we have divergence at this one. We have divergence at this one. Right, so we have divergence at this here. Okay, we look investigating at the boundary point. For the other boundary point, because the absolute value of 2, if absolute value of x is related to 2, we're interested in investigating plus or minus 2. So obviously at this point, we're going to investigate 2 exactly. What happens with 2 exactly? Okay, these are the boundary points of the interval. So now we have to investigate for x equals 2. We have, right, I'm looking at the an overview of the whole structure, exam structure. But these are the most important things in this module because everything is centered around this. But yeah, we're going to have a discussion about those other question one things, arbitrary proofs and your methods of proof, your contrapositive, your converse, your whatnot, inverse, and so on. For x equals 2, we have what? We put into the original series, which is minus 1 to the power r, 1 over 2 to the power r, x to the power r. So, which is minus 1 to the power r, which is 2 to the power r, the square root of r, and then we put 2 to the power r. Okay, in the place of x here, we have put 2, exactly, because we are investigating what happens, we're investigating exactly what happens at x equals 2. And therefore, this is this series here. Okay, this is a little bit tricky at x equals 2 because it's still alternating, so we need to use the alternating series test. We're just going to elaborate on that one just now, but it is, you can write it like 1 over the square root of r, which is of the P series type, but the P series is not alternating. Right, I just have power, I just had load shedding now. Hello. Um, um,